Okay, so welcome to the science class, and we were talking about work and energy, right? So let us see what have we covered so far. We have covered work and we have covered energy, and in this class we will look at the interconversion of mechanical energy, and then finally we will look at the rate of doing work. So let us start off with laws of conservation of energy. Now you know that energy can be easily changed from one form to another, right? This we can tell from the chart we had seen in our last class. And you must also know energy can neither be created nor be destroyed, right? Then what happens to the total energy of a system during or after the process? Like whenever an object is doing some work, if we consider the entire system, what happens to the energy? Is the energy lost while doing work, or do other objects gain that energy lost due to work by some other object? What happens to the total energy of a system? So to find out, let us consider an object of mass m falling from a height h, right? And here we will mainly talk about the mechanical forms of energy, which are the kinetic energy and the potential energy. So this object having mass m is falling under the influence of gravity. This object is falling under the influence of gravity towards the earth, and this falling is called as free fall because there is no obstruction in its path. So when the body is at the top, when we are just about to let it go, the body is at rest, and the entire energy that it has is only potential energy, right? And its value is mgh, right? From the formulas we have learnt in our earlier class, the value of this potential energy or PE is mgh. Now we let the object go. What will happen? It will fall down, right? And when it is falling down, it must have a certain velocity, right? So if an object is having a velocity and also it has mass, what kind of energy it must have? It must have kinetic energy, right? When a body is in motion, it must have kinetic energy. And also, as the height is decreasing while falling down, the potential energy of the system, the potential energy of the object must decrease, right? As the height is decreasing gradually, the potential energy decreases. And how can we say that when a body is moving, then also it has some potential energy? How can we say that? Actually, we can imagine the falling process as very fast steps where the object comes and rests at one point, then again rests at another point, and then again rests at another point, right? We consider the fall as infinite steps, right? We actually model or think the falling as the object is falling in infinite steps. Object is coming and stopping at a point, then again stopping at a point, then again coming down and stopping at a point, like this. We can imagine the falling like this, and we can tell that while it is having a kinetic energy, it also has potential energy with it due to the height, right? Now as it starts falling, potential energy decreases and kinetic energy increases. And how can we say this? You will observe, when we just let it go, it starts off very slowly, but when it hits the ground, it is actually faster than how it had started, right? It hits the ground faster than how it had started. So let us see how the PE and KE changes. So when the object falls down to 0.75 times of height, which is 3/4 of the height, when the object comes down to 3/4 of the height, now the object has the potential energy of mg into 0.75 h, right? Because that is the height at which the object is, mg into 0.75 height, right? And now it has gained some velocity, right? While it was falling down, the object has gained a certain amount of velocity, and let us call that velocity as v1, because we don't know what it is, right? So at 0.75 height, we have the kinetic energy as half mv1 square. Now the object has both ke and pe, right? It has both the forms of mechanical energy. So we can tell the net energy or the total energy of the system is mg into 0.75 height plus half mv1 square. This is the entire energy now the object has, right? This is the entire energy the object has now. And as it falls further, suppose it comes at half the height, 0.5 of height. Now the new potential energy is mg into height by 2, and let's call the new velocity it has reached as half, the new velocity is v2, and the new kinetic energy therefore becomes half mv2 square, right? And here also the total energy of the object is mgh by 2, which is the potential energy, and half mv square, which is the kinetic energy. So this is the total energy of the object now. And also, as it moves down further to 1/4 of the height, 0.25 times of height, and similarly we again get the potential energy as mg into 1/4 of height plus half mv3 square, the new velocity at height 0.25 h. And finally, when it hits the ground, height is 0, and so potential energy is also 0. mg into 0 is 0, and the object now entirely has kinetic energy. The object has half mv square as the kinetic energy, and we are considering the final velocity to be v, as we have always considered for the motion of any object, right? Final energy we have considered as v. So the final energy of the system or the object is half mv square. Now where did that potential energy go, and where did this kinetic energy come from, right? Actually what has happened, while falling down, potential energy gradually got converted to kinetic energy. Potential energy decreased and kinetic energy increased, and you can see for every velocity v1, our velocity after 0.75 height was less than that at a lower height, which is 0.5 h, v2, which was still lower than the velocity we had seen in the last slide, v3, at 0.25 height. And the maximum velocity is when the object hits the ground, right? So gradually kinetic energy has increased and potential energy has decreased. So let us see from the initial point. Here we had mgh as the total energy. At the next point, at a lower point, we had mg into 0.75 h. So we have lost 0.25 times the potential energy, right? We have lost 1/4 of the potential energy. And where has the 1/4 of PE gone? It has been converted to kinetic energy. This is mg plus 0.75 h, and this half mv1 square, the value of this would be mg into h by 4, or 0.25, right? And if you add these two, you can see we get mgh only, right? 0.75 plus 0.25 gives us 1. So the part of potential energy has been converted to kinetic energy while it is falling. Now as it falls further, here you can see half of the potential energy is remaining. So half has been converted to kinetic energy, and therefore as you can see half of the potential energy has been converted to kinetic energy. Therefore kinetic energy has increased. Earlier it was 1/4, right? And now it has become half. So kinetic energy has increased. Therefore V2 is greater than V1, right? And after this, as it comes lower, the PE, the potential energy, gets lower further, and you can see here it is 0.25 H or 0.25 times of mgh, the net potential energy. So the net kinetic energy here is 0.75 times of the potential energy, right? Because the net energy is always conserved. The potential energy has been getting converted to kinetic energy as the object is falling down, and now the kinetic energy is 0.75 times the potential energy, which is greater than the earlier one. It was 0.5, right? So as the kinetic energy is greater, now V3 also must be greater, right? It is greater than the earlier one. And finally, as it hits the ground, entire potential energy has been converted to kinetic energy, and now half mv square is directly equal to mgh. Half mv square is equal to mgh. You can see that gradually as the object falls, the potential energy gets converted to the kinetic energy, right? And as more and more potential energy gets converted, kinetic energy gradually increases in steps, right? Kinetic energy gradually increases. So while falling down, due to the decrease in height, potential energy decreases, but due to increase of speed, kinetic energy increases. And here you can see directly how one form of energy gets converted to another form, and here the conversion is taking place within the same form of energy, right? It is taking place between mechanical forms of energy only. Potential energy is one form of mechanical energy, kinetic energy is another form of mechanical energy, right? So the conversion is taking place within the same type of energy only. This can also take place, and this example shows us that energy of a system is always conserved. You can apply the concept of potential energy and kinetic energy to any object, any question you can get, and you will always see that the total energy of the system concerned is always conserved. Suppose you take two bodies colliding with each other. If you make two balls hit one another with some speed, you will see that their initial kinetic energies and their final kinetic energies will be same, because they are colliding on the same plane, right? They are on the ground only, they collide on the ground. So their initial energies and the final energies, the sum of them will be always constant. So we get to know here that if when we are considering a system where the transfer of energy is taking place, for that system energy is always conserved. Now let us come to the next topic, rate of doing work, or how fast or how slow we are doing work. Do all of us work at the same rate? Of course no, right? Some of us work faster, some work slower, right? And every individual is different from one another, so everybody cannot work at the same rate. And obviously a stronger person may do certain work in a relatively less time, right? If a person is strong enough, he can do a work very easily, right? With less effort. He can do work with less effort, and he can do the work very efficiently, right? So you can see the strength actually gives us a hint how the person's rate of work is going to be, whether it is going to be fast, whether it is going to be slow, right? Let us see one more question. Two machines consume or transfer energy at the same rate, and this is also no, right? Because we have different electrical instruments of different ratings, some 100-watt bulb or 60-watt bulb, right? Every equipment is different from one another until they are of the same type, right? You can have 4 60-watt bulbs and actually they consume the same amount of energy. So you can see machines also do not consume or transfer energy at the same rate. And here, a more powerful vehicle would complete a journey in shorter time than a less powerful one, right? Like when you have a car, obviously a sports car is better in terms of speed than an ordinary car, right? Or we can say the engine of a sports car is more powerful, right? It has more energy in it, so that it can move faster, it can do work at a faster rate. So let us concentrate on this word. When an object has power with it, when an object has power with it, it can do a work very easily and very fast, right? So rate of work is actually termed as power. Power is defined as the rate of doing work or the rate of transfer of energy. This is the definition of rate of doing work, which is called power, right? It is the rate of doing work or the rate of transferring energy is called power. So let us see what is the formula, or how can we define this in a mathematical statement. Power can be defined as work divided by time. Power is defined as work divided by time. Or you can easily say that it is the rate of doing work. Whenever we divide something with time, it shows us the rate of doing work. Like when we were talking about speed, we were talking about the rate of change of displacement, right? When we were talking about velocity, rather, when we were talking about velocity, it was the rate of change of displacement. So power, you can see, we can write easily as work divided by time or work per unit time, and by symbolic representation we can write P equals W by T. And so by rearranging this formula, we can get work is actually equal to power multiplied with time. Work is equal to power multiplied with time, right? And we will use these equations in questions coming in the next slides. So the SI unit of this rate of doing work, which is the power, right? The rate of doing work, which is power, the SI unit is watt. It is named under a famous scientist whose surname was Watt. You can look up in your book. The SI unit is given as watt and its symbol is W, right? And don't confuse with the symbol of work and the symbol of this unit. This symbol W is used after having a numerical value, and when we are using variables in a formula, we use W as the symbol for work. So be careful while using the unit and the symbol for work. So 1 watt is defined as 1 joule per second. You can see if the unit of power is watt, unit of work should be joules as it is in SI unit, and time it should be second. So watt, the unit watt can be defined as joules per second. So 1 watt can be told as 1, the numerical value, and the unit joules per second, right? 1 watt is equal to joules per second. And now let us talk about average power. What is it? As we had talked about average speed, which was total distance traveled by the total time taken, here also we are applying the same concept, total energy consumed by the total time taken. We can't just add the individual ratings of each instrument, individual wattage of each instrument, and then add them up to get the average power. We should always look at the total energy consumed in a given span of time divided by the span of time. This gives us the average power. So let us use this concept in a question. Two girls, each of weight 400 Newton. Okay, the weight is directly given. We need not calculate it with the acceleration due to gravity. Weight is directly given. Two girls, each of weight 400 Newton, climb up a rope through a height of 8 meters. We name one of the girls as A and the other as B. Girl A takes 20 seconds while B takes 50 seconds to accomplish this task. Or girl A takes 20 seconds to climb up the rope of 8 meters. Girl B takes 50 seconds to climb up the 8-meter rope, and they both have the same weight. So what is the power expended by each girl? What is the power expended by each girl? So you can see the force applied by them to go up is equal and opposite to the weight, right? They are actually going against their weight or the gravitational pull. So the force which they are applying on the rope to go up is 400 newtons, right? So they are applying force of 400 newton to go up, right? And their displacement is also towards up, right? So we know force, we know their displacement, so we can get work from here, and we are given the time, and we need to calculate the power, which is the rate of work or work divided by time. We have the work known, so we divide it by time to get the power of each girl. So let us see how to do it. We have made a column so that we can do the similar calculations for girl A and girl B at the same time to compare them. So both of their weights are 400 newtons. The height climbed by both of them is the same, 8 meters. Work done must also be the same, right? Force times the displacement, 400 into 8, 3200 joules, which is for both of them, because both of them are doing the same amount of work. Now the time taken only differs. A takes 20 seconds while B takes 50 seconds. So the power consumed will be work done by time taken, in this case 3200 by 20 gives us 160 watts, while 3200 divided by 50 gives us 64 watt. You can see due to the difference in time we are getting different amounts of power or different amounts of rate of doing work, right? Also you can tell the person who is, if both are doing the same amount of work, the person who is doing the work faster is more powerful, right? The person doing work faster is more powerful than the other one. So girl A has more ability to accomplish the task at a faster rate than B. This is the interpretation of the answer from the wattage given here. And by the way, we call this ratings as wattage for different electrical instruments. So let us see at the commercial unit of energy. The unit joule is too small, and hence it is inconvenient to express large quantities of energy. You will find that the joule is actually a very small unit when you talk about the electrical equipments used in your home. All the electrical equipments consume a large amount of energy, and if you express that in joules, you must have a long line of zeros following a certain number. So that is very inconvenient to use, right? So we need a bigger unit. So a bigger unit of energy is called kilowatt hour. We use this unit for commercial uses. We use kilowatt hour. So let us see what this unit actually is. And for information, kilowatt hour is not an SI unit. It is just used for commercial purposes, for just noting down the energy consumption in your household. 1 kilowatt hour, as the unit tells you, it is kilowatt and hour. 1 kilowatt hour is defined as 1 kilowatt times 1 hour. So you can see the interpretation is very simple. Kilowatt hour is simply 1 kilowatt times 1 hour. And if we want to convert it into joules and see how much 1 kilowatt hour is, 1000 watt is nothing but 1 kilowatt, right? And we can convert hour into SI units too, which is 60 into 60 seconds, right? 1 kilowatt hour has been converted to its SI unit, 1000 watt, and 1 hour has been converted to its SI unit, seconds, 60 into 60 seconds. Now if we find the value of this, we will find the value of the numerical ones separately and the units separately. Watt into second, as you can recall, power into time was work, right? And so power into time, the unit of it must be joules. And if we work it out, we will get 1 kilowatt hour equals to 36 lakh joules. 36 lakh joules. You can see how big this 1 kilowatt hour is. And in a scientific form, we can write 3.6 into 10 to the power 6 joules. This is a shorthand notation or the scientific notation we use. Okay, so you can see 1 kilowatt hour is a very big unit, a very big quantity, which is 36 lakh joules, right? So I think you can imagine how small 1 joule of work is compared to 1 kilowatt hour of work. And the energy used in your household and many industries and commercial establishments are usually expressed in kilowatt hour. The units or the power which you consume in your home, the energy you consume electrically in your home, is often given in kilowatt hour. And often we don't write kilowatt hour. We use different terms to write the same unit, kilowatt hour. Electrical energy used during a month is expressed in terms of units. You will see in your electric bill, you will often find 3 units, 4 units, 10 units, like this is the energy consumption, right? All the energy consumptions has been given in units, or we can tell 1 unit means 1 kilowatt hour. instead of writing this big unit kilowatt hour, we have shortened it and written it as 1 unit. And unit is actually used for electrical appliances, for the measuring of the energy you use in your household, right? So whenever now you see the electric bill, you will know how much energy you have consumed in joules directly once you understand how many units you have consumed, right? You will find out how many units you have consumed, you will find out how much kilowatt hour that is, and you can convert directly that kilowatt hour into joules, because you know how much 1 kilowatt hour is, right? 3.6 into 10 to the power 6 joules. So let's solve one question based on this. An electric bulb of 60 watt is used for 6 hours per day. Calculate the units of energy consumed in 1 day by the bulb. So you can see we are given watt and hour. So if we convert watt into kilowatt and multiply it with hour, you will get the units in kilowatt hours, right? So you know what to do here. You can find the energy in kilowatt hour, and then you can convert it into units. And you actually don't need to convert, you just write units in place of kilowatt hour because both of them are same. Power of the electric bulb we have converted into kilowatt, we have divided by 1000, right? And time used is 6 hours, and you can see we are not using SI units here. Why? Because for finding units, how many units we have consumed, we have to convert it into kilowatt hour, and directly we can find out how many units we have consumed. So here we have kilowatt, here we have hour. So now what we do to find the energy? Kilowatt into hour, right? Power into time taken is the energy. Power into time taken is the energy. 0.06 kilowatt into 6 hours. We have just put the values in the respective places. 0.6 kilowatt into 6 hours gives us 0.36 kilowatt hours, and 0.36 kilowatt hour is nothing but the same units, 0.36 units, right? 1 kilowatt hour is 1 unit, so 0.36 kilowatt hour will be 0.36 units. So we have finally got how much energy we have consumed in 6 hours using a 60 watt bulb. The energy consumed by the bulb is 0.36 units, right? So in this class we have learnt about the rate of doing what, right? And the commercial unit of energy, the kilowatt hour. And also we have learnt about the interconversion of energies, right, from one form of mechanical energy, the potential energy, to the kinetic energy. So for better understanding of these topics, you can always log into Webcoach. You must follow your school textbooks, your NCERT books, and for further practice you can always go for the TMH group for practicing science questions. So thank you and see you again.